Good morning, everyone. We'll get started back reviewing some problems. So this is from the chapter 7 to 9 review packet. I put up a second packet that we'll get into once we finish a couple more problems out of the first packet. This question here is asking about NO2 minus in terms of its best Lewis structure. So let's count our electrons. So that gives me 18 valence electrons. So central nitrogen, 2 oxygens. So at this point, I've used 16 electrons. So the 2 left over onto nitrogen. And then nitrogen right now has a positive formal charge. So it should have 5 electrons for a neutral charge, and it has 4 electrons closest to it. So those 4 electrons there. And so that gives it a +1 formal charge. And so we can reduce that formal charge by making one double bond. So we make a double bond here, move the electron pair off oxygen into a double bond. And so then that reduces the formal charge down to 0 and 0 for that N and O. The other oxygen, 6 minus 7 for -1 formal charge. And then, of course, we would have resonance if we were thinking about resonance. So both bonds in the nitrite ion would be the same. So we'd have this resonance. I don't know if we need those arrows, but the double bond can resonate over to here, making the 2 double bonds equal in bond length. So the nitrogen-oxygen bond lengths here are the same length. And remember, the molecule is never A, it's never B. It's not like a back and forth. It's at all times the electron pair spreads out and resonates across the molecule. So the real bond probably looks something more like this, where we can describe this bond here as being maybe a 3/2 type bond, 3 pairs of electrons spread across the 2 bonds, and the bonds being equal in length. I don't think we too often ask about the charge of oxygen, but the formal charge of oxygen would either be -1 or 0, averaging out, so to average out to -1/2. In terms of the formal charges on the O's, the formal charge of nitrogen, 0 in both structures, so that's averages out, of course, to 0. So the formal charge of nitrogen in the best Lewis structure. Now, another word you often see used here is probably not best. Maybe dominant is another word you see used a lot. And whenever you see the dominant Lewis structure, that just means which one is the best Lewis structure. So that would have a 0 formal charge. So there really is no other than the 2 resonance structures that are equivalent, other than those 2 Lewis structures that look identical. There's no other Lewis structure that we can write. So there's no other possible Lewis structure. Like the one without the double bond, if we had the nitrogen-oxygen single that we started with here, like this isn't a reasonable Lewis structure at all, because we don't have an octet around nitrogen, we have a formal charge, we can pull the pair of electrons in. One last thing we might mention is just getting into chapter 9 would be what geometry do we expect for NO2 minus, because we have 3 total domains. So we have a non-bonding domain for one, and then each of the bonds for the other. So we have 3 domains. So 3 domains should go trigonal planar. So we have trigonal planar electron domain. Geometry. And then the molecular geometry is just the shape of the atom. So we think then what's the shape of the O to the N to the O. Anytime we have 3 atoms, just remember 3 atoms is either linear or bent. This structure here would be bent. For it to be linear, the bond angle would have to be perfectly 180. So it'd have to have 2 total domains for it to be linear. So we have 3 domains, so this is trigonal planar. And then in terms of bond angle here for the O to N to O, it's kind of a lot going on in this figure here, but this bond angle, we'd expect it to be approximately 120 degrees. We have a bond pair, probably making it slightly less than 120. So we might be a little less than 120 here. So probably like 118, 117. So whenever we're predicting bond angles off of their perfect 120, or if we're in like ammonia and trigonal planar, and we're predicting 109.5 degree bond angles, the electron pair might kick it a couple degrees off of what we expect off of perfect trigonal planar 120. So pretty close to 120, but slightly less. Okay, so let's move off this question here. So which atoms below releases the most energy upon absorbing an electron? So absorbing an electron is electron affinity. And so this would be the atom, like phosphorus, absorbing an electron to go to the negative charge. We'd have argon absorbing an electron to go to argon minus. And so the argon atom here, because it's a noble gas, and the other choices aren't noble gases, this is going to require the absorption of the most energy. And so this would have to absorb the most energy, not release the most energy. The group that releases the most energy when it absorbs an electron are the halogens. So that would be something like chlorine, absorbing an electron to go to chloride. They're the best because they're capping off their shell. They're relatively the smallest atom in the row that has room for another electron. And they also have a relatively high effective nuclear charge, so they have a charge to pull that electron in. And so halogens are really good here. And so then the nitrogen group is particularly bad, and then also the NS2 group is particularly bad. So like the magnesium group are bad because the magnesium group has to put the electron in a higher energy subshell, and then the nitrogen row has to spin pair. I don't think they'd really go there with this type of a question per se, but you might recall that ionization energy had some anomalies in the boron group and then in the oxygen group for basically the same reason, but in reverse. If you're taking electrons away from boron, it has a 2p subshell compared to magnesium with the 2s subshell. So it's a higher energy subshell, easier to remove an electron than it was for magnesium. But then we go to carbon, nitrogen, harder to remove electrons, smaller atoms, higher effective charges, but then oxygen spin pairs. So spin pairing destabilizes the orbital, makes it easier to ionize an electron out. So for ionization energies are periodic inconsistencies in the boron-oxygen group, the NP1, the NP4 column, and then electron affinities that are more positive than you might expect from left to right is the magnesium and nitrogen group for the same basic reason. Okay, so still to answer this question, chlorine is the one that would release the most energy because it's in the halogen group. The electrons in which orbital of a magnesium atom experience the greatest effective nuclear charge? And so magnesium's configuration is a 1s2, 2s2, 2p6, 3s2. And so that's sitting on top of magnesium's 12 plus charge. So you have a 12 plus nucleus. So the 1s electrons are closest on average to the nucleus. So they're the ones that are going to experience the highest effective charge. So they see the highest charge in the nucleus. So the answer to the question would be the 1s. But then they're screening some of the charge from the 2s, so they'll see the next highest charge. The 2s electrons experience the next highest effective charge, then the 2p electrons, and then finally the 3s valence electrons experience the lowest overall effective charge. And then the lowest charge here is going to be experienced by the electrons with the highest N, with the highest L. So like when we start thinking of like, something like iron, with the argon 4s2, 3d6, that it's the 4s2 electrons that experience the lowest effective charge. And so the largest electrons, the 4s shell, experience a lower effective charge, so that's why when we go to iron 2+, that those are the electrons that we lose first. So iron 2+ would be an argon 3d6, because we're removing those lower attracted electrons first. And then if we go to like iron 3+, just make sure we see this, that iron 3+ would be a 3d5. But then we go to the next highest shell. So highest N with the highest L has the lowest overall attraction to the nucleus. Sometimes we ask like for how many unpaired electrons, so 3d6 would have 1, 2, 3, 4, 5, 6, so 4 unpaired electrons, and the 3d5 would have 5 unpaired electrons. All the electrons being spin unpaired in iron 3+. So sometimes we ask for the unpaired count just to make sure you have the right configuration and then the right idea of still applying Hund's rule for electrons distributing into those orbitals. So kind of the same question as earlier, but which atom requires the greatest amount of energy to be absorbed to lose one electron? So this is just another way of saying which has the highest first ionization energy. And so we have our choices: magnesium, calcium, oxygen, sulfur. So we're comparing magnesium, calcium here, and then oxygen and sulfur over here. And so our ionization energy is increasing from left to right. It increases left to right generally due to the decreasing size, increasing effective nuclear charge. And then we did have that periodic inconsistency, but that's like when you're maybe comparing nitrogen and oxygen, not when you're comparing far away elements. So oxygen is certainly going to be a lot higher than magnesium. Magnesium and calcium have generally lower ionization energies, being metals on the left side. And so our choices are really between oxygen and sulfur here. And then we have to go to our top to bottom rule. So for comparing ionization energies for top to bottom, we get the general decrease as you go down a row because the atom becomes bigger. The electron's further away from the nucleus, easier to remove. And so IE1 tends to decrease from top to bottom. So oxygen would have the greatest ionization energy for the choice of atoms here. Okay. And so, so I kind of left this one on here just as a reminder. We covered using bond enthalpy charts to approximate delta H's in chapter 5. So this is chapter 5 question, so we're not testing this again for chapter 8. It does appear in chapter 8 as well. It's a weird topic on why it appears in 2 chapters. Historically in our book, it had been in chapter 8, and then recently they moved the topics into chapter 5. And so we covered this back in chapter 5. So let's not dwell on this question here. The only nuance you might have for this type of question would be on the final, where in chapter 5 we didn't know how to do Lewis structures yet. So in chapter 5 we were showing you Lewis structures. When we revisit this topic, or if you see it on the final exam, we'd have to interpret, Cl2 is a single bond, F2 is a single bond. We'd have to think of the structure as ClF3. It's all single bonded too. But so just maybe a little bit more work is needed when we revisit this topic later, if it shows up in the final, just where we can sketch the Lewis structures, or you guys can work those out instead of having them shown. All right, so this orbital here, now we're not told too much information here other than the picture of the orbital to try to think about what this orbital might correspond to. Well, the first thing is that these look like s orbitals, meaning that there's no lobe in the orbital itself. So the orbital itself appears to be due to s orbitals. Now, I don't know if it's a 1s or a 2s. I don't know if this is the hydrogen versus helium 2 antibonding orbital, but this is antibonding orbital because there's no electrons being placed in between the nuclei. So the dots are referring to the nuclei of the atom. And so this type of orbital is kind of like breaking what was a bond. So this is an antibonding orbital, and then it's an antibonding orbital involving s orbitals, and it's also symmetrical about the bond axis. So the orbital isn't like a planar bond, but it's a symmetrical bond-symmetric bond, and so this is a sigma type bond, not a pi type bond. And so this would be a sigma star. And so this to me looks like it's probably the antibonding orbital for hydrogen. So hydrogen, H2, has the sigma 1s bonding orbital, and that orbital would look kind of something like this, where the electrons are most probably located between the nuclei, so the greatest shading would be in the center, less shading outward. And so that would be the sigma 1s bonding orbital, and then this might be the sigma 1s star antibonding orbital. This could also maybe represent the sigma 2s star antibonding orbital for things like lithium-2, beryllium-2, getting into the second row as well. So if this were, and there might be other pictures or other slides that we could talk about this some more, but like a pi star orbital would we'd have to see what looks like a pi bond, or a p orbital, I mean. And then the center is the nucleus, so we'd have to see like a bigger lobe on the outside, and so we have the greater shading away from the nucleus, so that's antibonding, and then seeing kind of that nodal plane through the nucleus of the atom here that would indicate that these are p orbitals. And so this would be a sigma 2p star orbital. And then if we saw the type of bond that looked like the p orbitals vertical relative to each other, and if they were overlapping in the middle, the picture here kind of looked like this, that this is our pi bonding orbital, And then our pi star orbital kind of looks the opposite, where the p orbitals are bending this way. Kind of looks like almost like a butterfly, but the p orbital is bending away from the nucleus, so our greatest shading further away from the atom. This is our pi star. Just in terms of recognizing some of the shapes of orbitals. And so bonding orbitals put the electrons are between the nuclei. Antibonding orbitals, the electrons are opposite. They're away from the nuclei. The net result of a bonding in an antibonding orbital are what we tend to think of as being non-bonding electron pairs. So let's construct a diagram here for O2 with a negative charge. And so that's going to be over here. So we use the diagram for O2 and its ions. What's going on over here is that this is just one of the O atoms. This is the other O atom. In the case of O2 with a minus, one of these might be O minus, the other might be O neutral. What goes on over here, we don't necessarily need to do this. This is just thinking that that's the electron count for oxygen, 6 electrons. So O minus would be 7 electrons, and the other O would just be neutral. And again, if I put these electrons in there, that's fine. If I don't, that's okay, because what I'm really trying to do is describe the orbitals in the middle. That's where I have O2 minus. So I just really need to make sure that in the middle, I put the electrons in correctly in the middle. Whether or not I really get and place the electrons in the atomic orbitals, because we're trying to think the atomic orbitals overlap with each other to make these molecular orbitals. The key of our diagram is putting in the proper number of electrons, so 2 times 6, but then plus 1 for the charge, so I'm putting 13 electrons in. If you notice here, I have 2, 4, 6, 7 electrons. Here I have 6 electrons. Just making sure I see that I'm just really placing 13 electrons into the diagram from low to high energy. So I go 2, 4, 6, 8, 10, 12, 13. And so I end up with 1 unpaired electron. It asked me to calculate a bond order. So let's calculate the bond order here. So our bond order will be 1/2 times the total number of bonding electrons. So here are my bonding electrons. They're the electrons that go down. They're the electrons in the orbitals that bring the electrons in between the nuclei. And then these are my antibonding orbitals. So I have 5 bonding electrons, and then minus the 2, 4, 5. Oh, I wrote this wrong. I have 8 bonding electrons, so 8 electrons in red, and then minus the 5 antibonding electrons gives me a bond order of 3/2. So my bond order for O2 with a negative charge would be 3/2. Now, a few other things that we can look at for the diagram might be labeling the diagram in terms of what orbitals these can be labeled as. So this orbital here would be my sigma 2s. It's a bonding orbital, so that's why there's no star, and it's from the 2s orbitals, so that's why it's a sigma 2s. And then it would look like that orbital we showed before. It would look something like this, where the greatest shadings between the nuclei. We have the sigma 2s star, which would look a lot like the orbital we sketched on the previous page. Then we have this sigma 2p, and then the pi 2p, then the pi star 2p anti-bonding, and the sigma star 2p anti-bonding. We sketched the pi bonding and anti-bonding on the previous page. I think the only orbital we didn't sketch on the previous page was the sigma 2p bonding. So just imagine this overlapping with this, where these are our bond centers. And so the orbital might just look like smaller lobe, big lobe in the middle, small lobe here, and these lobes are the nuclei of the atoms. And so this would be our sigma 2p bonding orbital. So when you're trying to decide if an orbital looks like a sigma 2s or sigma 2p, you're just looking for like lobes around the center of the orbital where there's a node through the radius of the atom, or a node through the center of the atom. And if so, then that's a p orbital. If not, it's an s orbital. There's a couple other questions. Which, according to their MO diagrams, which molecule below is diamagnetic? So we're looking at B2, C2, and O2. Now, we may not even need the diagram to know O2 is paramagnetic, but just to double check for O2, 12 electrons in, 2, 4, 6, 8, 10, and then 12. So I still apply Hund's rule. I put 2 electrons spin paired into different orbitals to spread them out in the molecule. So I have unpaired electrons, so O2 is paramagnetic. On the previous page, O2 with a negative charge would be paramagnetic as well. One or more unpaired electrons is paramagnetic. Diamagnetic is all spin paired. So the difference between paramagnetic and diamagnetic molecules is the paramagnetic molecules are pulled into a magnetic field. The diamagnetic molecules are not. They're actually weakly repelled, but I think the best thing to think is if you have a magnet and you have something diamagnetic is it's not being pulled into that magnetic field. And so then for B2, so boron has 3 valence electrons, so boron's configuration is a 2s2, 2p1. So we have 3 electrons for boron over here, same over here. So I have 6 electrons going in for B2, 2, 4, and then 6. So boron also, like oxygen, is paramagnetic. Because it has 2 unpaired electrons. It's a weird molecule in a lot of ways. It has a bond order of 1 if we were asked for bond order. And where that one bond, the single bond between boron, which you might think of a Lewis structure, would look something like this. So these are the non-bonding electrons that results from the bonding versus anti-bonding canceling out. And so for boron, an interesting picture is that we make the bond, like this bond here, has electrons between the nuclei of boron. And then when it comes for the p orbitals, they would rather put electrons here and then here. Because think about boron. Boron's different than, say, oxygen. It doesn't have a very high charge, has electrons already in the way that repel each other, so it uses the p orbitals instead to put electrons to avoid or minimize electron repulsions. When we get to O2, it says, you know what, I can actually put 4 electrons between the nuclei because oxygen has such a high charge. So the effective charge of oxygen helps it.
On the web.
I don't know what makes her do that. That's peculiar. But anyways, so for B2, it's peculiar in that it has a single bond that's made up of like 2 different type of pi bonds. It's like one electron in 2 different pi bonds. But so that's B2, and then C2 just puts 8 electrons. So we spin pair the electrons. So C2 here ends up being the diamagnetic molecule. All electrons spin paired, not drawn into a magnetic field. So another question has us ranking bond lengths. So for C2, O2, F2, B2, and we're being told to consider their MO diagrams to make this ranking, or we're actually asking which one has the longest bond. And so if we go back to C2, where we had 8 electrons going into the molecule, so here we have a bond order for C2 of 1/2 times, we have 6 bonding electrons, so here are our bonding electrons, and then minus the 2 anti-bonding electrons for a bond order of 2. So C2, double bond. O2 is also a double bond. If we go back to our O2 structure that we had earlier, so we have 8 bonding electrons, and then we have 4 anti-bonding electrons. And so the bond order for O2 would also be 2. So double bond. So probably not the longest bond with the double bonds. F2, if we do that next, so F2 would have 14 electrons. So we put 2 more electrons in here. So for F2, we now have 6 anti-bonding electrons. So the bond order for F2 would be 1/2, 8 minus 6, for a single bond. So F2 is exactly as we would expect from a Lewis structure. So from our Lewis structure for F2, we would have had fluorine with 1 electron here unpaired, the other fluorine the same, pairing up their spin for a single bond. So that's the same picture we get from the MO diagram. So for F2, single bond should definitely be longer than the double bonds. And then B2 is also single. So if we go back to boron, so boron would have had this configuration here. So B2, just like we had before, is also single. So now the question would be, boron and fluorine, both single bonds, which atom's bigger, boron or fluorine? Size decreases towards fluorine, so fluorine's smaller, boron's bigger, so the bigger bond here should be the single bonds. So F2 and B2 should be longer, but then B2 is even longer due to boron just being a bigger atom. So our bond lengths here should go B2 bond being the longest, then F2, and then we can apply the same trend if we wanted to rank O2 and C2, that C2 is longer because carbon's just bigger than oxygen, and then O2 is the smallest atom with the least bond order. So single bond's longer, double bond's shorter, triple even shorter. And then if we have two bonds of the same type, if we're comparing two single bonds or two double bonds, we can just look and ask the question, which atom's just bigger? Question on geometry. So which molecule is T-shaped? So a T-shaped geometry comes in trigonal bipyramidal electron domain. So it's the case where we have 3 bonding domains plus 2 non-bonding domains. And so some of these we may know easily in terms of like CF4, we've done this a bunch of times, but 4 plus 4 times 7 for 32 electrons. So CF4, in fact, we could have ruled CF4 out, right, because it doesn't even have the right number of bonds. It has 4 bonds. We need something with 3 bonding domains. It's going to have at least 4 bonding domains, no non-bonding domains, because we have all of our electrons used. So no lone pairs around carbon, so this is tetrahedral. But then SF2 also can't possibly be the answer, right, because we can only get 2 bonding domains for SF2. We can only get 2 bonding domains for SO2 and SF2. So the answer really has to be BRF3. Just based on it being the only possible molecule that can have 3 bonding domains. Now, if we want to double check, we would have 7 times 4 for 28 valence electrons, so central bromine, 3 fluorines, lone pairs around the fluorines. And then that uses all but 4 of the electrons that go in the central atom. So there's our 2 non-bonding domains and our 3 bonding domains. SO2's 18 electrons, looks just like NO2 minus, so SO2 would be central sulfur, oxygen, double bond oxygen. This is just kind of going back to the base diagram or Lewis structure we saw for NO2 minus, same count of electrons. Then SF2 would be 6 plus 7 times 2 for 20 electrons. So for SF2, there'll be sulfur, fluorine, fluorine, lone pairs on the Fs. For 16 electrons, the 4 left over go on to sulfur. 0 formal charge for sulfur, fluorine all the way around. SO2 minus has that weird case where maybe we can consider making a second double bond to reduce the formal charge down to 0, whereas if I left it here, this formal charge is positive, minus 0 over here. We have resonance as well in SO2 minus. So all the bonds are the same length in SO2 minus. So we would have 2 different Lewis structures for SO2 minus, where we could say this is the Lewis structure, the best Lewis structure that's not expanding an octet to minimize formal charges. And then the other Lewis structure being the formal charge Lewis structure, where we can minimize formal charges. So one thing for like if we're considering this structure here to minimize the formal charges down to 0, is you can only even consider that if the central atom here is in the 3rd row or beyond. So like if our central atom's nitrogen, let's say, then we can't expand the octet of the central atom. So, okay. So there's a few more questions here. I think this starts to get into the new packet I put up. So if you're looking for where these questions are at, they're in lecture slides, just a second packet. So here we're ranking the nitrogen-nitrogen bonds in the following compounds in order of increasing length. Let's start with the 2 in the middle. Nitrogen is just a triple bond. If we're not sure, we're just going maybe back to nitrogen dot diagram, and then pairing up for a triple bond to give each atom an octet and also 0 formal charges. And so then for N3 minus, we have 5 times 3 plus 1, that's 16 electrons to distribute. We have just to connect the 3 linearly. There's no other choice. 3 atoms just go in a straight line. Well, in a line. We don't know if it's linear or not. We'll see that once we finish our Lewis structure. And so then we do 16 electrons, so 8 each around the outer nitrogen. So that's all the electrons we have available. So we have a 3 plus formal charge on nitrogen. And so we can pull in a double bond. And then that would take us to here. So then this formal charge on nitrogen would be, oh, I added an electron pair. No electron pair on nitrogen. So I now have a 2 plus formal charge. I started with -2s on these nitrogens here. Why -2s? We should have 5 around nitrogen for a neutral charge. We had 1, 2, 3, 4, 5, 6, 7 electrons around each of those nitrogens on the outside of the molecule. So I started -2 plus 3 -2, probably not good. So I make 1 double bond. I now get a -1 plus 2 -2. And so then what do I do next? Well, I probably want to minimize this down to -1, reduce this down to plus, so I make another double bond and make 2 double bonds on both sides. This reduces down to -1. So I go -1 plus -1 across the molecule. And then that rule I was talking about in the previous slide, that we cannot expand octets of second row atoms. So the structure that I cannot do, so I can't do this again. I can't get to this structure here. Might look like a good Lewis structure because I've made 1 other double bond and I've reduced the formal charge down to 0 and 0, but I can't expand the octet. That's too many electrons. That's 10 electrons around central nitrogen. No room for those electrons. So this would be my best Lewis structure with double bonds all the way around the molecule. Now, if for some reason we wanted to go with the triple bond over to here, like let's say we thought, well, why not this? Puts a -2 over here, puts a plus over here, but reduces, what did I do? Reduces this nitrogen down to 0. So we might be thinking, this Lewis structure here, not too bad. This isn't necessarily a bad Lewis structure because we're still minimizing magnitudes of formal charge, but we just kept minimizing the same nitrogen's formal charge. Well, we'd have resonance over to the other nitrogen, right? So we just resonate over to here. So being plus, now this being 0, this being -2. And then what would that average out to? It would average out to that structure. It would average out to the 2 double bonds. So if we do think maybe it should be triple and a single, but triple and single would resonate to triple and single on the opposite side, which would average out to double and double. So I'd say this structure here would be our dominant structure. And it would be more representative too, showing the 2 nitrogens equal in length, both double. And so then if we're ranking our bond lengths already, this is going to be the shortest because it's the triple. And this is double, so this should be in the middle. And then NH2, NH2, hopefully this is single, because otherwise we might have a hard time answering the question. But NH2, NH2 would just have 2 hydrogens on nitrogen, and then nitrogen's connected here. And then in terms of electrons, I have 2 times 5 plus 4 times 1, so that's 14 electrons. And I've used 2, 4, 6, 8, 10. So I have room for electron pairs on nitrogen. So I put 2 electron pairs on each nitrogen to distribute the remaining 4 electrons. That also gives me the count I should expect for nitrogen. We said a few times before, nitrogen likes to form 3 bonds in a lone pair because that gives it an octet and 0 formal charges. And so this gives us the single. So this should be the longest bond of the 3 because it's single. So in increasing length, 3 should be the longest. And then 1 should be in the middle, and then 2 nitrogen, the shortest with the triple bond. So tricky question that we're going through a lot of different structures and trying to think about bonds in terms of single, double, triple here. So triple bond for N2, N3 with a minus charge was double bonded, and then NH2, NH2 was single bonded. What's the molecular geometry for this molecule here? Well, our electron domain geometry would be 1, 2, 3, 4, 5, 6. We have 6 total domains. So that would be octahedral electron domain. And so then if I have octahedral electron domain and I replace one of these spots with a lone pair, then I get one pyramid about a square plane. So this would be square pyramid, so square pyramidal shape. So you could memorize 5 bonding domains, 1 non-bonding is square pyramidal, but if you can see the shape and just imagine what the shape might be called, that would be helpful. So I'm just trying to picture octahedral, replacing one of the spots with a lone pair. Now only did trigonal bipyramidal have the case where if you put the electron pairs either here or here, you get 2 different structures. So only trigonal pyramidal do we have to do some thinking in that we replace the structure that goes seesaw. So I don't put the electron pair here, I go seesaw with 1 non-bonding domain. So, but that's the only geometry between, trigonal planar, tetrahedral, and octahedral. Only trigonal bipyramidal do we have the issue where we're replacing 4 bonding domains, 1 non-bonding domain. Which domain do I choose? I put it on the trigonal plane. If I have 2 electron pairs, I also add it to the trigonal plane and go T-shaped. And then I also replace another if I go 3 for linear for things that have 3 non-bonding domains and 2 bonding domains. For octahedral, if we have an extra electron pair, it goes opposite the other electron pair on the same axis, so we go square planar for the case of 4 bonding domains, just to make sure we're kind of seeing the shapes and the reasoning behind the geometries that we see across trigonal, bipyramidal, and octahedral. I think we've seen a question kind of like this before, but this question here is looking at which of the molecules are polar, or which of these molecules are nonpolar. So all of these bonds here involve phosphorus and fluorine or phosphorus and chlorine. That bond is certainly polar because we have, one of the more electronegative atoms, fluorine or chlorine, bonded to an atom that's not particularly electronegative of phosphorus. So in all of these cases here, we're developing partial charges across the molecule. So for the first one, I get the same negative charge on every end of the molecule. And so that is the definition of nonpolar. So compound 1 is nonpolar. Compound 2, now I put 2 chlorines opposite each other. Those dipoles cancel. Then I put fluorines in a trigonal plane. Those cancel. Like if I had a molecule that was like this shape here, that would be nonpolar. And if I had a molecule like BF3 or whatever in a trigonal plane, this would be nonpolar. A molecule like this might be something like CO2 is nonpolar. And it's kind of like you're putting those 2 molecules together here and also making a molecule that's perfectly nonpolar. So you end up with like a linear set of bonds that cancel, a trigonal plane set of bonds that cancel, also perfectly nonpolar. But then if I put the chlorines where they're not opposite each other, now they're 90 degrees relative to each other, now what happens is that the negative charges here are not exactly the same as the negative charges on the fluorines. I have a different charge on like the left side of the molecule versus the right side. Now this molecule here is polar as a result. It's this, you may be looking saying, well, there's still negative charge on every end of the molecule, but it's not the same negative charge. We need the negative charge to be exact. Like if I'm looking at CF4, and I have fluorines all the way around the molecule, this is nonpolar. But if I replace those fluorines with any other atom, if I replace just one of these with like a chlorine, then that becomes polar. All it takes is breaking that sort of symmetry in the molecule, and then all of a sudden we have a polar molecule, because we don't have exactly the same charges. And one of the ways I try to explain this, if you imagine putting a positive charge here, this negative end can fly towards that charge and win the battle for it. If we go back to having the fluorine here in a nonpolar molecule, then all those atoms are fighting over the negative charge, and the molecule can't just like have one end of the molecule win the fight. It just spins relative to the charge. And so that's one way you can try to envision what it means to be polar versus nonpolar. And then if I replace having all chlorines around the molecule, certainly this molecule here will be nonpolar. So 1, 2, and 4, perfectly nonpolar based on the geometries of the molecules and the arrangement of the bonds. Compound 3 is polar just because we don't have the proper symmetry. So we don't have the 2 chlorines opposing each other in the right way. So we have different charges on the ends of the molecule. So we can still have negative charges on the ends of the molecule, we just can't have, it just has to be the same exact negative charge for the molecule to be nonpolar. There's another question that gets at molecular polarity, kind of going through the range of a bunch of different geometries, I think on the next slide. But let's just look at a couple examples before we get there. SO2, so again, 18 electrons. We might remember the NO2 minus example, but in case we forget, we just start central sulfur, connect the oxygens with lone pairs, and then count our electrons used. That's 16 electrons, 2 left over, onto sulfur. So that kicks it into being a bent bond. Being bent trigonal planar kind of helps us here because it's not linear. If it were linear, if it were like CO2 and linear, then that would have been nonpolar. But because this bond is bent, it's going to allow our oxygens to, have a negative charge. Let's make one of our double bonds here to go to 0 and then plus, and then -1 over here. And so for our structure here, we have negative charge building up on the oxygens. So the negative charge is either 0 or -1 averaging out to -0.5. So the oxygens are negative, the sulfur is positive. So I have a negative end of the molecule, I have a positive end of the molecule. Don't let the electrons, sometimes students see the electrons and say, well, aren't the electrons negative? It's like, well, they are negative, but they don't really, we're looking at the buildup of charge in the atom. The atom is big, the electrons are so small that they're not pulling things in based on the size and location. It's this positive charge here that sees through, that other atoms can be attracted toward that positive charge. These electrons are too small to get in the way of that positive charge being seen by atoms. And so just note that these charges here, negative, and then not the same negative charge over here. It's actually positive. So I have a positive charge here, definitely a polar molecule. Now again, if we had something like CO2 where it's linear, then this is nonpolar. Because the two oxygens oppose each other, I have two negative ends that are the same charge. ICl5, this is kind of like the Lewis structure that was on the previous page, 7 times 6, 42 electrons. So this is like the square pyramidal molecule. So we have chlorines attached to iodine. And then electron pair. So we have the square planar geometry. Certainly going to be a polar molecule because we don't have a chlorine on top of the molecule to counterbalance. So we have negative charge on the bottom of the molecule and on the sides, but not on the top. And so I'm building up a partial positive on iodine. So I have a positive charge on the top end of the molecule, negative charge on the bottom end, certainly a polar molecule. So the slide I was mentioning, I'm just going through a few different types of geometries. So BF3, nonpolar, all the bonds canceling each other out because we're trigonal planar. So you have to think of the shape of the molecule. Linear or diatomic molecules are easy. Just for a diatomic molecule, two atoms, you just have to have two different atoms bonded together that differ in electronegativity. So the HCl bond is certainly going to be polar. If we have CH3Cl, if we had replaced this with another H, it would have been nonpolar. So if this is an H, it's nonpolar. If all of these are chlorines, it's nonpolar. But if they're not all the same, the molecule is certainly going to be polar. So CH3Cl is polar, ammonia is polar, electron pair here, positive end of the molecule, or excuse me, negative end of the molecule on the electronegative nitrogen, partial positives on the hydrogens, CCl4 being nonpolar. Let's do another ranking structures on bond lengths from Lewis structures. So we are told that that we're going to obey the octet rule with these Lewis structures. And then we're going to rank the sulfur-oxygen bonds in increasing length. Let's start with SO. So SO, maybe we haven't seen this before, but this is really just like O2. This is just having 12 valence electrons for a diatomic molecule. So this, we could just be thinking is something like this, oxygen something like this, pairing up for a double bond. So we have SO double bond here for our Lewis structure for SO. SO2, we just did it on the previous page, but let's think about resonance for a minute. So we have this structure here. And then we can have the resonance over to here. So we have resonance kicking in. And so we should have the 1, 2, 3 bonding pairs of electrons spreading across the 1-2 bond. So this should be 3 bonding pairs. Spread across the 2 SO bonds. So that's a 3/2 type bond. And then SO3, central sulfur, 3 oxygens. Let's count up our electrons. 6 times 4, 24 electrons. So this ends up with a 3 plus formal charge on sulfur, minuses on the oxygens. So we can satisfy the octet rule by making 1 double bond. So we make a double bond here. Let's move this pair of electrons in to here. Let me clearly write that as a double bond. And then this changes our formal charge for sulfur to now be +2. Should have 6 electrons surrounding it, only has 4. And then the other oxygens stay negative. And so then here what we have is the resonance over to here, and then the resonance over to here. So we have 4 total bonding pairs. Spread across the 3 SO bonds. So we have a 4/3 bond, which is 1.33. That's going to be the longest bond. So it's the other way. So that's going to be the longest bond because it's closer to single. Then we have the 1.5 bond, and then the 2 bond being the shortest. So the SO should be the shortest, SO2 in the middle, SO3 for the shortest bond. Here from our prediction from these Lewis structures. Now, sometimes 4/3 versus 3/2, it's kind of always reminds me of the funny story on how Burger King, have you ever heard the story? Burger King tried to compete with McDonald's on the 1/4 pounder, and they had a 1/3 pounder, and it failed miserably, and they did a poll to try to figure out why their customers didn't like the 1/3 pounder. Do you guys know why it failed? Because people were like, well, it's less meat than the 1/4 pounder. It's like, okay, our public doesn't understand fractions, but we do. So 4/3 is a lower bond order, so longer bond. 2 double bond being the shortest here. In terms of the numbers, so once it's in increasing order, SO3, 1's the longest, 2 in the middle, and then the shortest being 3. Okay, so that's all the questions I had prepared. Is there any particular topic anybody just wants to throw out that we can talk about for a couple minutes before we wrap up today? Is there anything that feels like we haven't talked about? I think the one thing that you may be wondering that we haven't, or there's like 2 basic problems that I don't think I did an example of like specifically. That would be like the Born-Haber problem, working one out. I don't think you're going to see that again. We saw one in lecture, we saw one on a recitation activity. Those are kind of proof of concept problems to see how it is you calculate and how like a lattice energy is determined experimentally is through like a Hess's law cycle of other known values. So it's not a directly determined value. So just trying to understand that process was why you saw a couple examples, so just appreciating that. So I don't think we're going to throw you data to calculate a lattice energy like you saw on those 2 types of problems. So those are kind of proof of concept problems. Also, like the dipole problems where we give you a bond length and a dipole moment, calculate charges. Those are kind of a proof of concept too, because I like to use those problems to, 1, show you what it means to be partially charged, how big and partial positive and partial negative. If we recall, HF got to about 0.4. So we're not getting close to +1, -1 with our partial charges, even for a really polar bond. It's giving us an idea that partial charges are probably in the order of like maybe 0.1 to 0.15 units of charge being shared across a polar bond. So probably not a type of problem you'd be expected to solve on a test, but just one where we're thinking bond length as it relates to charges. Higher charges, longer bond gives you a bigger dipole moment. I think we can just end early unless somebody wants to throw out anything they want to talk about for a couple minutes. good luck tonight. I think this test is easier in some ways than midterm 2. At least these concepts are all coming together into like a single set of topics. So I think chapter 7, 8, 9 go well together. Hope you guys do well tonight. Whenever you take the test, good luck. See you on Wednesday.